All right, let's talk about when exponents are fractions. We've been working with simplifying exponents. We've been working with simplifying radicals. As it turns out, exponents that are fractions are radicals. So that's the connection we've been trying to make with you guys. So in other words, what you're going to see, say on a test, is somebody saying, hey, what's 9 to the 1/2 power? Rather than just going to a calculator and typing that in, we need to start to understand that. It turns out, just keeping things basic, it turns out that means the square root of 9, which is 3. So if somebody was to say, what is the 81 to the 1/2 power? That means the square root of 81, which is a 9. Adding a little bit onto that explanation, it turns out that this 2 that you're seeing on the denominator of that little fraction is actually asking you what two numbers multiply to make this number 9, and that's where the 3 comes from. And again, what two numbers multiply to make 81? It's 9. So I should say a number times itself. So what happens when fractions are different than 1/2? Say 27 to the 1/3 power. What's that going to mean? Well, again, now we're looking for 3 of the same number that would multiply to make 27. And what times what times what gives you 27? It turns out that's what we mean by the cube root of a number, which in this case would be the number 3. Another example, 125 to the 1/3 power, and that would be the cube root of 125. So what number times itself 3 times would give you 125, and that number is 5. 5 times 5 times 5 is 125. Of course, things do get slightly more complicated the more you understand these things. So let's say, for example, I say the number 16, and this time I'm going to put it as the 3/2 power, so that's the fraction 3/2. What's that going to mean? Well, the 2 on the bottom still means I'm looking at square root of 16, but what does the 3 in the numerator do? What do I do with that? Well, it turns out, I guess the easiest way I can explain that is we can throw some parentheses around that, and that 3 becomes the exponent of that. So now we can look at that and go square root of 16, well, that's just the number 4, but to the 3rd power. And 4 to the 3rd power is 4 times 4 times 4, or 4 cubed, and that's 64. I didn't mention that on the first problem I did. The first problem I did was 9 to the 1/2 power. I didn't really need to mention it because the 2 did mean a square root of 9, but if I put an exponent of 1 out there, that just really doesn't do anything. That's still going to give me 3 to the 1 power, which of course just gives me 3, so I didn't need to mention it before. So now we should be a little bit more comfortable to write a general rule for how to deal with fractional exponents. So the rule is going to be this. If I have a number with an exponent that is a fraction, I'm going to say m over n. Remember, I'm just keeping things general. M just means numerator, n is the denominator. We can write that as a radical where the n is what we call the index. That means the root, like square root, cube root, 4th root, and so on, of the number. And then we can put parentheses around that, and then this becomes the exponent out there. In fact, you might prefer it to sort of just think of it like this. So some number with fractional exponent, this is the denominator is the root, and on top is the exponent. Therefore, you can say that we have the root, and then whatever the number or letter is goes there, and then you can put the exponent out here. Okay, so I hope that rule makes sense, but I do need to add a little bit onto it. There's actually sort of an alternative version of each one of those. We still do the nth root, but that exponent, which is the numerator of the fraction, can actually also go inside the square root on whatever's in there. So over here, that would be, we can still do the root, but then you would put the x, and the exponent can actually go down with the x. That's going to help us on the next thing. So sometimes you'll be asked to convert radicals into rational exponents. There's some good reasons to do that sometimes. So here we go. So an example of that that you might see on a test would be, let's say, the cube root of 27x squared times y to the 6th power. And so remembering our rule, we can understand, I guess, that there's really 3 parts to this. There's the 27, there's the x, and then there's the y. So the exponents, instead of writing, cube root, we can say, well, 27, there was an exponent of 1 on that, and then there's the little 3 out here, so that makes the fraction 1/3. So 27 to the 1/3 power. And then the x has a 2 there over the 3, so that's 2/3. And then the y gets 6 over 3. And now that we have that in that form, we can say, well, 27 to the 1/3 power, that does just mean cube root, and it turns out that 27 is 3 times 3 times 3, that's a perfect cube, so I'm going to say 3. X to the 2/3, there's nothing I can really do with that, but here you'll see on this y that that's 6 over 3. That can actually reduce, which was kind of the whole hope as we started this problem, that something would sort of get a little bit nicer looking. And there's sort of a final rewritten answer for that. There's just certain mathematical reasons to convert like that. Let's try another one. Let's try the square root of 16x to the 4th y cubed. Now remember on square roots that there's an imaginary little index out here of 2. Sorry, that looks like a 3. That's a 2. Square root. And so as we rewrite that, that's going to be 16 to the 1/2 power, because that's what square root of 16 means. We have x to the 4 over 2, and yes, that's going to reduce here in a second. And then we would have y to the 3 over 2 power. Now let's simplify what we can. 16 to the 1/2 power means, what number times itself is giving you 16. That's 4. And then x to the 4 over 2, that reduces. 4 divided by 2 is 2. And then the y has an improper exponent. There's not much I can do with that. That's just 3 over 2, and we're done with that problem.